Welcome to the next lecture in this series on condensed matter theory. In this lecture I want to talk to you about mean field approximations. And then in the next lecture we will continue with looking at a few concrete examples, the Hartree or Hartree-Fock approximation, or the Hartree and Hartree-Fock approximation, and density functional theory. So there is a clear reason why I put a capital of an S behind approximations, because there are different ways you can do your mean field approximation. So what we've seen in previous lectures is that we can look at our Hamiltonian within an approximation that the atoms are fixed in space and neglecting all kind of relativistic effects, which are small. We can add them later. They're not going to change the basic ideas that we introduce. But if we look at our Hamiltonian, we have the kinetic energy, the interaction between the atoms, the interaction between the electrons and the atoms, and then the interaction between the electrons amongst themselves. And it is this later part that leads to entanglement between your electrons. When one electron moves, all the other locally react to it, and this gives rise to exponential scaling of the Hilbert space with respect to the number of electrons. So it is this last part of the Hamiltonian that we want to replace by an effective potential, which is the mean field potential that we have. By doing so, we can generate particles that look like electrons but not necessarily have all the same behaviors as the electrons. And in order to find optimum approximations, we should allow to say that we are also allowed to, for example, change the kinetic energy of the quasi-particles by changing the effective mass. We have seen that particles in a periodic potential behave as new particles with a new mass. And the same can happen when particles interact with each other, that can give rise to new effective masses. So what we had before is our bare electrons, described by the full Hamiltonian. Once we go to a mean field approximation, we start to talk about quasi-particles, where when this is a real potential, there are real particles, but if you take into account that you have some scattering, then your Hamiltonian might even become complex, and then we talk about quasi-particles with finite lifetime. So the question that we want to address here is how to obtain our effective potential. And in the lectures today we will keep m equal to the original mass, but we will introduce at some point also a correction to our total energy due to a change of the kinetic energy of the quasi-particles. So we are looking for a potential that gives you an optimal representation of the original problem. The answer is never going to be really the same. It's always an approximation. It's never going to be exact, but we want to optimize this. We can say from our full Hamiltonian there is a ground state such that A psi is E0 psi. We have our mean field Hamiltonian given by the kinetic energy plus a potential energy, and we can also calculate the ground state of that mean field Hamiltonian. Psi mean field 0. Now we can define our potential such that, for example, we maximize the overlap. We maximize the overlap between our mean field ground state and our many-body ground state. Well, in practice, this is a really unpractical way to define your optimization scheme, because in order to calculate this overlap, you would need to know the many-body wave function, and the many-body wave function scales exponential in system size, so it's very hard to represent the many-body wave function and therefore to calculate this. Even if you would say, I'm not optimizing this for all systems, but I'm looking at a subsystem, then still calculating that many-body wave function for a subsystem of reasonable size is very hard. And therefore, this is not really a practical way. Instead of looking at the wave function, we can say, well, I'm going to calculate the total energy of your system. And then I'm going to minimize, for example, the mean field ground state. And the nice thing is that I do not even need to know the many-body ground state, because I do know that the lowest energy state is the eigenstate, is the ground state. So if I'm minimizing my mean field energy, I choose the potential such that this is a minimum, then I go to an optimal representation of my system. For sure you have to put on some restrictions on your potential, because making your potential just minus infinite is not okay. So in the end, you want to minimize the energy difference between the mean field ground state and the many-body ground state. And you know that you live in a world where the many-body ground state has the lowest possible energy of all states. Instead of looking at the energy, one can also look at the density. And one can minimize the ground state density, such that the difference between the ground state density minus the mean field ground state density is as small as possible. And here you have to define some norm. So you could look at the square and then integrate over whole space to minimize. Now these methods all look at the ground state. And if you want to look, for example, at the stable structure, then minimizing the ground state is indeed a smart thing to do, because that's what is determining the crystal structure. If you want to look at stiffness and strengths, then you look at the ground state, you minimize it, and you make small variations in the crystal structure, and you see how your ground state energy varies as a function of crystal orientation. So then also you're minimizing the ground state energy. Now if you make a photovoltaic device where a photon comes in and makes an excitation, then it is very important to know that the energy difference between the ground state and the excited state is reasonably represented. When you minimize the ground state energy, or you optimize your representation and your potential such that the ground state energy is the lowest, then you have it minimized in equally good terms the energy for the excited state. And therefore you should expect that in methods that minimize the ground state energy, the excited states are at too high energies. So if you look at excitations, you can better minimize energy differences. So we want to minimize E1 minus E0 compared to the mean field difference. So again, we can take the differences of the differences or the square of the differences of the differences and minimize this energy difference such that you optimize your potential to represent now not ground state energies but excitations. So you see there are several ways you can define your effective potential to optimize different parts that we have in our system. And in the next lectures I will have a look at a few different methods that we have. First, the Hartree approximation which in the end is not so useful as it violates the Pauli principle, but it defines a nice way to calculate an effective potential, and we can extend on this to get the Hartree-Fock approximation. And in the Hartree-Fock approximation, we normally minimize the ground state energy, but you can redefine the Hartree-Fock approximation to also look at energy differences or the states at finite temperature. And then we look at density functional theory. And in density functional theory, we have much more freedom to define functionals to optimize the representation of our state. Either look at energies or at densities or gradients of densities. And from there we can continue, and once you have these tools and understand what you can do with them, you can define many different ways to optimize. And there are many different ways around to optimize for different cases. Thank you very much. Stay healthy. We see each other in the next lecture.